let me first introduce Professor Ceyhun Bulutay. He is going to be talking about quantum information, quantum optics, and so on. So let me start with a brief introduction about him. He graduated from Middle East Technical University. Then he has a PhD degree in 1997 from Electric and Electronics Engineering Department of METÜ, working on computational many-body physics of 2 and 3-dimensional electron liquids. Then he did 1 year postdoc at University of California, Santa Barbara, working on excitons in white-gap semiconductors. Then he also joined for University of Essex, United Kingdom. Then he joined the Bilkent University Department of Physics. Then during his sabbatical year 2011 at ETH Zurich, he was working on spin dynamics in in-gas quantum dots and so on. Today, he will talk about, let me give the exact title, Quantum Information and Quantum Optics. Yes, that's the general one, that's what I remember. So the floor is, I'm giving to Ceyhun Bulutay, but I just want to remind that don't be shy, you can ask the questions. I guess he will provide his email address as well. Later on, you can always send an email, but don't be shy and try to ask your questions. If you feel not comfortable, even you can ask in Turkish as well. Please, Professor Bulutay.
Çok teşekkürler Oğuz Hocam. I also welcome everyone for this noon session. First, I would like to thank wholeheartedly to Ali Kram Hocam for organizing this very nice event. I'm already learning a lot from the morning sessions from Özgür Hoca and Cengiz Hoca. And also to TÜBİTAK again for organizing this interesting meeting, which is the preparation school for the upcoming workshop. What I will talk about is quantum information and quantum optics is a huge field. 45 minutes for each is kind of a joke, but I mean, having said this, one can really kind of highlight what goes into the into this field. So that's what I will try to achieve. And if you cannot follow this, or to follow this, let's say these two lectures, all you need to know is linear algebra and notation that is very common among physicists, the Dirac notation, which you would pick up, for instance, if you have taken at least the first half of an introduction to quantum mechanics. That's all you would need. So with that, let me now share my screen. Let's go with this and see if this is good enough. Okay. I hope my screen is now visible. I will go just like Özgür Hoca and write on this, with my not so good handwriting. And then I will share through, again, just like Cengiz Hoca, the Google Drive, where it is better handwritten and more details you will find. Okay. This will be just a scratch pad, what you will see here, but the better one will be in the Google Drive. Here's the outline. I'll start with what just a reminder to qubit, then the density operators, pure and mixed states, and then move on to bipartite systems and introduce Bell states, and then the entanglement and its measures. And move on to three-party systems and talk about some popular tripartite states J, Z, and W. And I would like to finish up with an application on quantum teleportation. So that is my ambitious plan. And tomorrow's plan is quantum optics. So this is my wake division. But you will benefit from this part also on the quantum optics part. So let's now remember what was a qubit. So a qubit or a quantum state, let's say, is psi, is just a vector in the vector space. Here we have for a qubit a two-dimensional complex vector space. So all there is linear algebra, and it's a two-dimensional vector space, spin 1/2 business. So you need to span this space, you need two basis vectors. The very common one is the Z computational basis, so to speak, which in the common notation in quantum information, these are the established notation for these two vectors, which span this space script V, let's say. So if this Pauli Z operator, remember the discussion from Özgür Hoca, acts on these eigenstates, they will be just producing the eigenvalues of these vectors plus and minus 1. Okay. And any vector psi can be expressed as a linear superposition of these basis vectors. Okay, and here alpha and beta, they are just some complex numbers, provided that their modulus sum adds up to 1, normalization business. And as you have seen in Cengiz Hoca's lecture, you can depict this on something called Bloch sphere. Any quantum state, any qubit can be expressed on the Bloch sphere as a vector. So let's say this is my vector psi, some linear superposition state, and the north pole is our one vector 0, and the other one is the south pole is the other Z computational basis vector. Okay, so using the standard notation from spherical coordinates, the polar angle theta and the azimuthal projection here, phi, you can just express this also using theta and phi, like this. And you don't need to worry about normalization now in this representation, already normalized. Okay, so any point on this Bloch sphere is a state, quantum state, qubit. Okay, now this I guess most of you know already. Now let me introduce the new thing in the game, the density operator. Okay, the notation that goes for the density operator is rho, and I use het for operators, just like the Pauli Z operator. Now, why do you use or why do you need a density operator? Because we want to know expectation values of some operator O. Okay, so I want to make a measurement on a quantum system which is in a quantum state psi, let's say. Then what you need to do is work out this expectation value, this matrix element. Okay. That is the expectation value of O. Sometimes we write this also like this. Now, another way of achieving this result, if it's observable, this is a real number that comes out as a possible probabilistic value of this, let's say. is through some operation called tracing. Okay, so let me now introduce this trace operator of some, it's a super operator, let's say, because it operates on operators. We will need this. Sometimes you see in the literature also this. Either one is common. I will go with capital T, so trace. Okay, so what does it do? It does the following thing. It's again a tool from linear algebra. It takes a matrix and just sums the diagonal entries of that matrix. Okay. In our terms, what it does is trace of an operator A. You just take any complete basis. Let me just denote this as a basis like this. Okay, and you just project or work out the expectation values of that operator over each member of your basis, and you sum them up, which is equivalent to, if you have a matrix representation in this basis, just summing up the diagonal entries. This is what we call as trace. It's a operation from linear algebra. Okay. And this is basis independent. Traces, it doesn't matter whether you use, let's say, Z computational basis, X, Y, whatever. It's just independent of what basis you use to do this computation. Here's the other thing. If you are in a quantum state psi, which we will call it as a pure state, this is going to become important. We will associate with this something called density operator as an outer product like this. Okay, so if you want to calculate some expectation value of an operator, which is simply this thing that you know, it is also equivalent to a trace of the density operator and the operator you are interested in. It's simply this product, and it's very easy to show that this is so. You just plug in, let's say, a basis, and just plug in this guy and O and this, and just move things around, which is the always common trick in summations. Move things around, and you're done. Let me just get rid of this. First, move this over here. It's just a C number, and then combine it with the summation. So if you do this, then you have something like this. Summation and another psi here. Okay, so this is just the resolution of identity, complete, all projections. So this is identity. So this is back to what you wanted. Okay, it's back to this. Okay, so let me just get rid of this. So if you know this density operator, then you know a lot. Okay, this is one of the main achievements. The density matrix tomography is actually in quantum optics, for instance, is very important. Okay, and all you need to do is once you have it, is just form out the trace, sum up the diagonal entries in some matrix representation. Okay, now that was for a pure state. Let's move on to something more complicated. Okay. A mixed state. Now, pure states, which is most of undergraduate quantum mechanics, is a huge idealization. Life is not as pure as pure state. And in reality, what you end up with is a mixed state. And all the engineering problems of quantum technologies are around these, dealing with these mixed state features. Okay, so what is a mixed state? It is just a statistical mixture. That's a good name, actually. I take a pure state like this, and I have a bunch of these. Let me just label them with K. And I just sum them up with some probabilistic, classical probabilistic weights. Okay, so that is what turns a pure state into a mixed state. If you have more than one term in the summation, it's now a mixed state. So if n is greater than 1, then it's a mixed state. So you are just here, there's a condition, the statistical weights must add up to 1. Okay, so a mixed state is a statistical mixture of several pure states, but it must be more than 1. Now, here comes the first thing to deal with. If you give me a density operator, let's say in some basis choice, it is a matrix. Okay. Can I tell whether it's pure or mixed? Okay. This is something practically quite important. Given a density matrix, how to know whether it's pure or mixed? And it's very simple to find it out. First thing, if you just take the trace of rho, because of normalization, it must always be 1, whether it's in pure state or mixed state. This is for sure. This is because of normalization. However, the trace of rho square is a check. If it is 1, then it is a pure state. If it is less than 1, then it is a mixed state. Okay. So all you do is take the rho, square that matrix, and that rho squared trace, if that is less than 1, then there is some statistical mixture that goes in here. At this point, for quantum information, we will actually combine this with something from information content. So that is the von Neumann entropy. By the way, we have a very elite crowd. So if there is anything that I say wrong, please, and somebody more knowledgeable than me realizes this, please intervene and let's correct this. So there is this von Neumann entropy also very handy at this stage. Okay, so again, you take the density operator and work out the so-called von Neumann entropy of it. It is defined as, so Özgür was using this for by definition symbol. Okay, so it's the trace of rho log rho, and there's a minus sign that makes things positive. Okay. Now, how do you calculate such a thing? It's very weird. Inside the trace, there is a logarithm and multiplying. Now, the easiest way one can calculate this is work in the basis, eigenbasis of the density operator itself. So in that case, in the eigenbasis of rho, this thing just, in the eigenbasis of rho becomes diagonal. And these are the just eigenvalues of the density operator, let's say K or let's say D. Okay. In that case, in the eigenbasis of density operator, then this simply becomes just an easy summation of the eigenvalues log lambda K. Okay. Now, these are details that you shouldn't bother at this stage, but the end result is important. For a pure state versus a mixed state, the entropy is different. In the case of a pure state entropy, von Neumann entropy, let's say pure, maybe that's over notation, it is simply zero. There's no entropy in that case. But if it's a mixed state, then the entropy is greater than 0. Okay, so there is some statistical mixture buried down. So that is the cause of increase of entropy in here. So this is yet another alternative of finding whether the system you are dealing with is a pure quantum state or a mixed quantum state. Okay, and reality is things are mixed, and that means all the proofs, all mathematical proofs, they are, orders of magnitude more difficult than pure state proofs. As in some cases, the proofs for mixed states are not available. In some cases, certain things, they were shown to be NP-hard problems. Okay, for mixed states, things are quite difficult. Okay, now there is something called maximally mixed state. Okay, so let me just coin this term, maximally mixed state. Okay, for a d-dimensional vector space or Hilbert space. A qubit is two-dimensional, remember. Okay, but it can be qubit, qubit, whatever. These are the jargons used. So a maximally mixed states density matrix is expressed to the dimensionality d as this, in this form. So this is a pure state, the output product of some basis vector I, and this is the statistical weight that we had introduced over here. Okay, so in here, the maximally mixed state has a very democratic mixture of the pure states. Okay, and it's matrix representation in this spaces is just 1 over d, 1 over d, all over the diagonals, 1 over d, zeros here. This is a maximally mixed state. Okay. Now, I will conclude this section of density operators, which is also something that you need in quantum optics as well, but it is even more important in quantum information, with the properties of density operators. The most important property, normalization. This guy, the trace of density operator must be 1. Now it's a Hermitian operator because its eigenvalues are probabilities, so it must be Hermitian. Okay, so that means the eigenvalues of rho, which actually in von Neumann entropy we use them over here, they must be real. Not only that, they must be, the eigenvalues must be non-negative. Okay, okay. So this is called positive semi-definite operator. And what else can I say? The mixture and or not, the trace of rho squared. If it is 1, it is pure. If it is less than 1, it is sorry for this. This thing is less than 1. This is mixed. Okay. So this is a quick wrap up of the density operators, and we will run into them once again. Now, let me introduce a bipartite system. That's next in my lineup. Okay. So far, I had a quantum system which had 1 qubit. Let me now have two systems. It's now a bipartite system, two-party system. Okay, and for this bipartite system, I have a qubit in the possession of A and another qubit in the possession of B. Okay, A and B, they may be separated or they may be at the same point in space. Doesn't matter. Okay, so I will first introduce something called Bell states, and then I'll move on to entanglement. So I have now a qubit at the position of A, another qubit at the position of B. Okay. So these Bell states, there are four of them because this bipartite qubit system is a four-dimensional space. Okay. It is two bipartite times the dimension of each one is a qubit 2. So it's a four-dimensional space. And I will just need to span this four-dimensional vector space. I need two vectors. Okay. Bell states are such vectors. They are just four vectors that span this bipartite qubit space. Okay. So let me just use the common notation that goes into Bell states. This is like the alphabet of quantum information. One of them is phi plus minus, the other is psi plus minus. Okay. For each sign, plus and minus, we have two different vectors. So let me just go with the phi. So 0, 0, plus minus 1, 1. This is one of them done. The other one is 0, 1 plus minus 1, 0. This is the notation. These 1 over square root 2s, they are there for normalization. If this guy is normalized, this guy is normalized, then this 1 over root 2 takes care of combined normalization. Okay. And this plus sign goes with this plus sign, minus sign goes with this minus sign. And another thing that goes into this notation, which is a very shorthand notation, is, let me just pick up this one. This thing is a shorthand for saying that the A qubit is in the 0 state and the B qubit is in the 1 state. Okay. Rather than writing all the time like this and putting here just for notational rigor tensor product, we just don't do this. We just simply write this in this fashion. And so this, locations are important. This is the A location. This is the B location of these qubits. Now, what are these guys? Now, these guys, they just span the space. Okay, it's a four-dimensional space. And these guys can represent any bipartite quantum state in this game. Okay. Yet you can have, these are called entangled states. We'll just talk more on those. So this is an entangled basis. A product basis, on the other hand, is very intuitive. You could have just guessed this is these four vectors 0, 0, 1, 1, 0, 1, 1, 0. This is a product basis. Okay. So here in these so these are Bell states, these are product states. Now these Bell states, they have a quantum correlation in placed, okay, imprinted to the quantum state. If state A is 0, the other must be 0. Or if state A is 1, the other must be 1, okay, if this is your state. And this phase in between is also crucial if you make some interferometry of these qubits. So this phase can also become important. This sign, you can say, or you can just upgrade this to some phase if you like, but not in the definition of Bell states. Bell states are defined in the way I have just written here. Okay, so now we seem to have some quantum correlation, and we have now two systems. And for those, for such a bipartite system, the density operator will have two symbols attached to it. This is the bipartite density operator. One very important thing that you will need, and we will in a minute use this, is how to get from this bipartite to that of A and B density operators. How do you achieve this? Okay, and that is very easy to achieve. Actually, the information contained in this joint bipartite density operator allows us to go in this way, but not the other way around. Okay, it is called, these are called marginal density operators. These are called marginals. It's nothing quantum here. This jargon is from good old probability. And just like in good old probability, if you want to go for the marginals, the reduced density operators, what you do is you take this guy, the joint probability, and let's say you want to go to row A. What you do is you trace out, so to speak, the B degree of freedom. You are ignorant to what the value B, what B takes as a value. Okay, this is going to the marginals. Likewise, if you want to go to the margin of B, you trace over the A degree of freedom. Okay, let me show you this quite easily, how you trace out this. I'll take one of these Bell states and find out its marginal. Okay, so let me take as an example, let's take the psi minus state, which is this guy. Minus. Okay. What is the associated density operator for this guy? It is just simply this. It's a pure state to begin with. We just need to work out this. Okay, let's do this. So two terms here, another term from the browse, and so you will have 4 terms. Let me expand these 4 terms. These are the minus sign, guys. Yes, I think I've done it correctly. So this is nothing but this outer product of this guy. At least if you don't know anything about quantum mechanics, cosmetically, you could just write this for aesthetic reasons, let's say. Okay, so this is our the joint probability operator. I will trace out the B degrees of freedom. I don't care about what is this value, the second guys. I'm just ignorant to those guys, okay? What I will do is, I'll just do the tracing let's go up. Just the tracing is done like this. I choose a basis and sum over the diagonals, okay? Okay, so let me now choose a basis. 0, the computational basis, this is for the B guy. and right here row AB, and also do the same for the other guy. Okay, when you do this, this is in the lecture note that I will post in Google Drive. Immediately you get this result. Okay, so this is the reduced density operator of psi minus. Now, is this pure or mixed? It's for sure a mixture, statistical mixture, 50% of this state and 50% of this state. It's a maximally mixed state, actually. So what did we have here is an entangled piece, okay? You had party A, party B, and they were in an entangled quantum state, psi minus, this psi minus state, okay? If one of them is 0, the other has to be 1, and if this one is 1, the other has to be 0. So they are in some entangled superposition, entangled state. Now, if you just are ignorant to what happens to the B side, then you are just throwing out quantum correlations. So what remains, behind is this guy. Lots of statistical mixtures. Okay, it's no longer a pure state; it's a mixed state. So if two objects, two parties are entangled, and if you are ignorant to this fact, then what is left behind is a mixed state. Okay, that's how mixed states actually are born. There are always interactions with your quantum system and the environment. Environment couples to your system. They get entangled, but you do not keep track of the environment degree of freedom. What is left behind is a mixed state. Okay. Now, how to find whether a state is entangled or pure? Okay, that's the next thing I want to show. Let's put the title, entangled versus product. How do you determine this? Okay. A product state is, let me write a product state because we have written the entangled state, and the product state was already in our basis, these guys. Okay, so there is no quantum correlation between the pieces. One of them is 0, the other can be 0, or the other can be 1. So there is no quantum correlation. Knowing one part doesn't tell you any information about the other part in a product state. And how do you do it? Let me write a general quantum state, AB, okay, in some basis, okay. I will use, let's say, the dimensionality of one of these guys is A, the dimensionality of the other parties, let's say, is B, okay. So I will write this as such a product state. So this is a product state. I would write this as AI, BJ, but just maybe, they are equivalent in my notation. So by product basis, you can represent any state in this bipartite system. That's what I'm doing here. And this is the complex weight that goes into that expansion. Now, if you just tell me this guy, the full, this is actually rectangular matrix, if dimensionalities of space A and space B, factor spaces are different, it's a rectangular matrix. So I take this matrix, the gamma matrix, the coefficient matrix, and I feed in to a linear algebra package called singular value decomposition. Okay, MATLAB, Python, all of them has this built-in singular value decomposition. You feed in this rectangular matrix, it spits out or just turns this into two square matrices, one rectangular diagonal matrix. It turns this into these forms. For us, what is important is this guy here. It's a diagonal rectangular matrix. A bit awkward. We are not so much familiar with rectangular matrices. So this is the A times the B matrix, and the diagonals, let's say, are consumed in one dimension, in one direction, let's say in A. Okay. So these are the diagonal entries of this singular value decomposition. And the way you find out whether some state is entangled or product is simply by counting these non-zero entries here, as simple as that. It's called Schmidt rank. Okay, so which is number of non-zero entries. If the Schmidt rank is 1, then this implies that your state AB is entangled. Sorry, it's a product state. And if Schmidt rank is larger than 1, then it is an entangled state. It's not only a single term like one of these, but it combines at least two terms like this. So it's an entangled state. Now, you can say, so what? But actually, entanglement is, what gives rise to the quantum power. Remember Cengiz Hoca's and also Özgür Hoca's lecture. Özgür Hoca concluded in quantum sensing that shot noise can be beaten if you use not product states, but entangled states. You go to the Heisenberg limits. You go from quantum standard quantum limit to Heisenberg limit by using quantum coherence and entanglement. So it's so important. And this is a measure of finding out the Schmidt rank, at least for pure states. Here what we have is a pure state. So this is actually for pure states. Mixed state is quite complicated. It's a different and very complicated situation. How do you quantify whether it's a separable state or an entangled state in the case of a mixed states? Okay, let me see what I can do at this point. I will skip, in the interest of time, GH set and W states. Let me, okay. I think it's better if I just don't take your time over time, and let me go to quantum teleportation. Okay, so please check the notes on GH set and W states. These are the generalizations of Bell states from dimensionality 2 to 3 and above. Okay, GH set, you can define GH set states or W states for it's a tripartite or above kind of entanglement. So these are entangled states of ABC. Okay, and they are very fragile. Okay. Okay, and there is also no cloning theorem. These are very important no-go theorems in quantum mechanics, quantum information. It's for an entangled pair. It simply says that you cannot, using entanglement, you cannot convey information superluminally from one spot to another spot. It's the no signal theorem. So special theory of relativity is respected, and this proof was in 1980s or so. So much later than the objection by Einstein, Podolsky, and Rosen, it was proven. And no cloning theorem is also very important. If you have an unknown quantum state, you cannot generate two copies of this, okay, without destroying the original. Okay, so these are really important, and they are kind of our guards in quantum cryptography, for instance. So let me, for the last thing for today's lecture, talk about quantum teleportation. This is the backbone of quantum internet. In the quantum internet, you have hubs. These are quantum nodes, and you want to convey from one node, it can be connected with a fiber, to the other, a qubit, not a bit, but a qubit. Now, no cloning theorem forbids sending a copy of this from A to B. So teleportation, quantum teleportation, gives us a recipe how you can connect send this quantum state, unknown quantum state, from a party here to another party here. These can be separated by thousands of kilometers or in space, whatever. Here's how you do this. The first thing is, let's say you have an unknown state at the position of A, and the Alice doesn't know what it is, okay? It's some alpha 0, beta 1. Alpha and beta are unknown. You're not allowed to make measurements, okay? You just store this in a quantum memory. And then the next thing you need is an entanglement between A and B. This must be pre-established, okay? Let's say A and B, they share a Bell state. I will just choose psi 5 plus. So in the position of A, let me just remind you what this was. It was 0, 0 plus 1, 1. Okay, so this is at the position of A, this is at the position of B, A, B. There's also this guy as well. So I will call this, all this thing, psi A1. So this is the A, second qubit of A. So A has two qubits. One is one pair from the entanglement, and the other pair in the position of Alice is the state to be teleported. Okay, so if you write this state, this product state, this is what we have. We have a product state in this situation. I will write this in a different form. I will write this, look at the A side. On the A side, I have two qubits. But a two-qubit bipartite system can be represented in terms of Bell states. Where is that? Look, I can use not the product basis, but the Bell state basis. So this is the homework that I will assign to you, that you derive the details here. There's another homework that is inside here. In the posted lecture notes, you'll see a homework buried in here. Another homework for you is to show that this can be written. This is the most complicated thing for my lecture today. You can write this as such. A1, A2, and alpha 0, beta 1, B. Another term, psi minus A1, A2, and this is multiplied with the B side, slightly different, and two more terms as psi minus and psi plus. Two more terms here. Okay, let me just fill them up for the homework. Now you can say, what is the logic of going through this mess? The point is, if you write the A position qubits in the Bell representation, you realize that this state on the B side, this one is exactly what you want to teleport. It's exactly this. Okay, so square of this, which is 1/4, 25%, B has the result at the position. Okay, so this is the desired state. The other guys, these are not desired. However, by simple gate operations, you can turn this one into this one, this one into this one. All of them can be turned into this one. For instance, this one is simply a Pauli Z operation acting on this qubit. It turns it into this one. So here's the protocol that Charlie Bennett and co-workers found. Alice, in the quantum teleportation, in the position of those two qubits, makes on those two qubits a Bell state measurement. That Bell state measurement can have one of these four outcomes. Alice looks at the outcome, and if the outcome is this one, then already B has the desired result. Already immediately this Bell state measurement is performed. There is a collapse of the, there was an entanglement. That entanglement will be consumed, and the B state will collapse to this one, the desired one. But if it is not this, but this one, then Alice already knows, if this is the result on the Alice side, she already knows what to do. If she finds out this result, she also knows what to do, perform Pauli X. Or if she learns that this is the outcome, she will tell Bob what to do. So what she does is, by classical communication, she tells Bob what to do. Keep it as is, or apply Pauli X, Pauli Z, Pauli X, or a combination of X and Z. So this is the protocol of quantum teleportation, and it's technologically something very crucial in quantum internet, and this has been demonstrated by quantum hardware. Okay, so when this is done, you consume this link, entangled link, and you destroy this quantum state at the position of A. It is destroyed, so you are respecting no cloning theorem. You are respecting no signaling, because for this protocol to work, there must be a classical communication between A and B. Okay, so which is in the, at most at the speed of light. It cannot be above the speed of light. Okay, so this nice teleportation protocol shows us a lot of details about physics, not only quantum physics. Okay, so maybe that is where I should, stop. Actually, in reality, there are always, in the fiber links, quantum channels, there are noise, and what you send, teleport, is not the ideal state, but it's some statistical mixture. So you can just quantify how good was your teleportation by something called fidelity.
Hoş geldin. Şimdi bir şey değil, bir şey yapıyorum şurada.
Okay, so also, I think I'll stop over here.
Okay, thank you, Ceyhun Hocam. Now we can have some questions. If you are, if you wish, you can ask in Turkish as well. Ceyhun Hocam will summarize the question in English.
I have also shared the drive link, a better handwritten version, and it includes more of stuff that I couldn't, squeeze into this an hour lecture.
John, but you should speak once again.
Yes. Tomorrow morning.
Yeah. Only one.
I couldn't get.
Tomorrow you should speak once again.
Oh yeah, oh, Hocam, yes, yes. That's on quantum optics. So this was my quantum information. So I have one more.
Next time we will give you several lectures in order you could completely express yourself.
Okay. So we're going over time.
Yeah, it's very nice. That was very nice. Evet, Oğuz Hocam, sorular geliyor mu?
Everybody is shy. But anyway.
Türkçe sorsunlar.
Şehirde e-mail adresiniz var.
Türkçe sorun arkadaşlar. Çekingenliğe gerek yok. Zaten biz bunu sizler için yapıyoruz. Bak hocalarımız gelip anlatıyor şu bu. Düşünürsünüz bu anlatan hocalarımız bizden para filan alır. Hayır, sıfır. Bak hepsi burada. Yok öyle bir şey. Sorun. Bunlar zaten sizler iyi yetişesiniz diye fedakarlıktan olan şeyler.
There is a question, Alikram Hocam. Can we do entanglement for any system that is not entangled? Sheva, that's a good question, which actually probes how do you entangle two systems? And as always, physics is about interactions. Okay, if a system A and system B, they interact, then that will cause an entanglement, okay, potential. And that entanglement can actually oscillate over time. So mainly it is an entanglement. If you want, I can give a more concrete example. Once again, let's go here. Let's just consider an atom, okay? You have an atom, the electron in the excited state, electron in the ground state. Now, if this atom is in isolation, then there is no entanglement. But if this atom is, let's say, interacting with the electromagnetic vacuum, then potentially it can interact with the vacuum fluctuations. It's a quantum object. So it can spontaneously emit a photon and recombine and go to the ground state. So this is just a very popular way of creating entanglement. Now this photon and this electron or the atom, they are now entangled because of this coupling to the vacuum. So you can write with some probability gamma, there is a decay. So now the new state is the entangled state of photon and atom. photon and atom, let's say, is this. There is a probability of decay. An electron is in the ground state, and in the universe there is, let's say, n+1 photons, plus there is probability of no decay, and electron in the excited state, and there is one less photon in the universe. So this is just an entangled state. It's not a product state. Okay, so bottom line is it's the interaction. Interactions, they create, entanglement.
Başka soru şu anda gözükmüyor ama yani sabah Ceyhun hocamız there is another one from Aydın. Ceyhun.
Are entangled states always needed to be created artificially? Can we observe entangled states in materials like superconducting oxides? Now, by artificially, I guess, already things are, the quantum objects, they are already interacting with one another. So you don't need to create them artificially. Any interaction that is already in the system dynamics will entangle them and disentangle them. Okay, it doesn't have to be some human-made interaction. If I got the question correct. It's actually hard to disentangle systems. It is hard to actually keep a system not talk to the environment. That's more difficult. So that's what makes a quantum computer difficult, right? You want to preserve your quantum data, and it should not be entangled with the rest of the environment.
Yes. Another one.
Entangled states store more information than product states. Now, I think that's a good question, definitely. So that is about entropy. So the entropy of a product state and entangled state. Okay. So my answer is yes. But that's a good question. I think that somebody can give you even a better answer than my answer. There's a question about from Ali Can. In quantum teleportation part, we assumed we have an established Bell state. That's a very good question, Ali Can. How do you generate this link? That's a technical detail, very important one. Just in a few sentences, let me tell you how. Okay, so you have Alice and Bob separated, and now in between you must have a source. Okay, a photon source, let's say, a photon source where a very popular one is quantum cascade with two actually via two let's say roots. Just get rid of this. A quantum cascade that happens either this way or some other way. Let's say this is sigma plus, sigma minus, or vice versa. These are just an atom that decays by emitting two photons. Okay, so if you do not know which path it has taken, either this path or this path, then these two photons they become let's say A and B. Let me just not get into the notation. They become entangled. So you are sending on either side two photons which are either this or vice versa. So you must have such an entanglement generator in between. And once these photons are captured by A and B, now those photons, they are entangled. This is at least one way of generating entanglement stored on A and B. Spontaneous parametric down conversion. You have to just take a look at, this is a cliche way of generating entangled photon pairs there, or bi-exciton cascade. That's another very popular way of generating entangled photon pairs. Usually it is the photons that are very, practical to generate entangled pairs. And also, Cengiz Hoca's very nice presentation, the NV centers, again, we can generate entangled photons from NV centers.
Today at 3 o'clock, we have a lecture from Alexander Serchenko. He will talk about how to engineer and use entangled photon states as well.
So, also, John.
A couple of more questions. Very quickly, can you?
Yeah, I see. The next one is Çağlar Aslan. If we have lab equipment, how can I demonstrate the quantum teleportation experiment basically? I think that's the fidelity. So you must have a known quantum state, not unknown, but a known quantum state, and pretend as if you don't know it, and then teleport this and look for the fidelity. If what you get is very close to what you expect, people always quote fidelity, the value which is very close to 1, that shows that you have a more or less successful quantum teleportation. Alper Uğur, can we measure entropy loss while ignoring entangled pairs in case of teleportation? Again, I think your question again is the measure. How successful is your teleportation? This has to do with fidelity. So yes, and basically, Alper, this is a very complicated field. That lots of competing measures, and people are writing papers claiming that there's a better measure and a better measure, especially for mixed states. You do not consume the possibilities. So some may be better in some certain aspect, but fidelity here is the first thing that comes to my mind.
Let's say this last question as well from Sarah.
Okay, for systems bigger than bipartite, there must be more complex entangled states than Bell states. Does it reduce the chance to get the desired state? Yes, exactly, in teleportation. So all those tripartite states are definitely so much fragile. In the homework example, you will see, that W state is more rugged to, loss of some particle. But the GH set is terrible for particle loss. By the way, also in the lecture notes, I gave you an assignment to quantum distillation. Quantum distillation is another technology which is very popular. So please read about quantum distillation.
Thank you, Ceyhun. So now let's have a break. Since this was a long day, we need a little bit more energy. So we will meet again at 3 o'clock for the lecture of Alexander Serchenko about the entangled photon states.